talking about here is they're related to one another, right? So let's think about what that says there. Simple harmonic motion, we said, is this type of motion, right? It's a spring with a Hooke's law relationship. And we said it doesn't necessarily, we said there's many types of oscillations that not necessarily a spring like this, but it could be a molecule inside of an atomic structure that's oscillating, or it could be some sort of a structure in a building that has a spring-like action that oscillates like a spring. It could be many, many things inside of some sort of mechanical system. So, but as we pointed out, we can use mathematical techniques. If we understand simple harmonics, we can use that maybe to analyze a more complex oscillation or periodic motion. Okay, so we'll go on here now. So simple harmonic motion then is the spring, but then they're relating it to uniform circular motion, which is something moving in a circle. Now they talk about this a little bit, and talking about Galileo, and he made some connections. But here's the essence of what they're talking about. You can think of simple harmonic motion. You can think of simple harmonic motion as the projection of uniform circular motion on the diameter of a circle in which the circular motion occurs. So here, for example, is a circle with a radius, and the radius they're defining as x sub m, and you have a point particle moving around the circle in a uniform speed. Uniform circular motion, right? And as you follow the motion of the particle, right, the angle that they define is omega t plus phi. And x, they're looking at x as a function of time, and this is the side adjacent to the angle, right? And so this becomes x sub t equal to what? This is x sub m. Here's an angle, omega t plus phi. This component is the cosine of omega t plus phi multiplied by the hypotenuse x sub m. And so you get x as a function of t. And so this is our equation for displacement for a simple harmonic motion. So what you're saying is you can model the simple harmonic motion in this sense as the movement of a particle moving in a circle. So as this particle moves, the x component, of course, shrinks, right? Over here it's shorter. It goes to 0, and then it goes negative, right? Reaches a maximum here, and then it goes back to 0, and then back to maximum. And that, of course, is a cosine function. You know, starts here at a max, goes to 0, goes to negative, goes back to 0, goes to positive, back to 0. That is P, the motion of a particle. It's the projection moving. P is a projection moving in simple harmonic motion. Here, P is a particle moving in a circle. Now, if we look at the velocity, then the velocity of something moving uniformly in a circle is what? It's a tangential velocity, isn't it? Right? As something moves in a circle, its velocity is tangential, isn't it? Yeah. So here is the tangential velocity. This angle geometry, you can figure it out. These are similar triangles. This is omega t plus phi. Here's my velocity, but in circular motion, then we know that that the velocity is omega times r, which in this case is omega x max, and we have so that's the length of this. This is the angle, and this is the we're looking at this projection. The velocity is this projection onto the x-axis. This is v as a function of t, so that is the sine function, isn't it? This projection is the sine. That's a little tricky, but it's the negative sign because it points in this direction. So we get v sub t. We get v sub t equal minus omega x max times the sine of omega t plus t. Okay, and then with regard to acceleration, centrifugal acceleration points to the center, and we know that that value is omega squared r. We know that acceleration is omega squared times the radius, and that the radius is x max. And so this projection, again, is the cosine. Yeah, this is the angle that's similar angle there. Here, this is the cosine, but it's negative because this points. So we're looking at projection. This is negative p sub t, and we get an expression for acceleration, which is minus omega squared x cosine omega t plus p. Okay. Well, anyway, they're just showing you that for a particle moving in a circle, it's the projection of its position, its velocity, and its centrifugal acceleration. The projection on the x-axis is equivalent to a simple harmonic motion. So if you, I don't know if I can do this. So if you take something in a circle, right, your shadow, right, even though my finger's moving in a circle, the shadow is going back and forth like simple harmonic motion. So that's a little tricky. But anyway, I hope you get that. Now, so now we talked here about damped simple harmonic motion. I don't usually cover this on the test, but we'll just talk about it here a little bit. I'm not going to get into it because we're late in the semester. So we're not going to test on it. A little bit unfair. So if there's a problem on these, and you would skip that if I gave you a problem like that, okay? But nevertheless, we'll just talk about it and kind of get some impression of the rest later. But so we have damped simple harmonic motion. What that means is kind of illustrated here. Here's a spring with a mass and it oscillates, and you dampen it if you have this attachment which is filled with fluid, and as this moves up and down, it slows down the motion. It dampens it. That's called damped simple harmonic motion, and the force of damping is proportional to the velocity, and it's inversely proportional to the velocity. And so in addition to F equals minus Kx, right? F equals minus Ks, you now have an additional term due to damping. You just have an additional term. It's velocity dependent, has its own constant. And they do a little differential equations here. They point out that the acceleration is the same. Would you not walk in front of the screen? Thank you. Just don't walk in front of the screen. Thank you. It's the second derivative of x with respect to time. And that's acceleration, and the velocity is dx dt, so this is your differential equation. You're probably familiar with that, maybe seen it. This is the solution to that equation. Standard solution, it's an exponential function with x and mass in it, with a cosine. So that looks like this. It has this envelope that conforms to